Morning.
Good morning.
Good morning.
Sorry about that, folks. I am here. Sorry, I was on the phone. All right, let's get started here. So I'm sorry about what happened on Monday. That was beyond my control. That was a national issue, or at least an East Coast issue for Zoom. It all went down, so I didn't get the chance to talk to you on Monday. So let's get into at least some of the stuff I was going to talk about, and what I was going to focus on today is everybody's favorite topic, which is, anybody want to guess what we're going to talk about today? Favorite topic.
Sig
Everybody loves
Figs.
them. Oh yes, Emily, it's all about Sig Figs. Oh, I can feel the excitement in the room. I can. I tell you. Oh, it's just wonderful. Let's go ahead and get started on this wonderful Sig Fig experience. Okay. So in module 3 is where you'll find this stuff about Sig Figs. I'm not really going to focus on the dimensional analysis portion of this. I feel that if you're doing the homework, then you'll get plenty of practice at dimensional analysis and using the conversion charts and all of that. So I mean, I might do a little bit of that, but not a whole lot. I'm going to focus mostly today on significant figures and then do a little bit of dimensional analysis and then get into the density module. The density module is relatively easy, but I do need to go through the significant figures to give a bit of context to some of the stuff we're going to see in density. Okay. All right. Significant figures. All right. Why are significant figures important? Well, that's what a lot of students are asking me, and why I always take off points for not having the right significant figures. Well, it's all about accuracy and expressing the accuracy of a number. And the whole point of significant figures is that you can't have a number more accurate than the least accurate number that you're using, or the least accurate thing you're using to get a measurement, which I think makes a lot of sense. You can't claim any more accuracy than the least accurate thing that you have. It's like a chain. The weakest link in the chain will tell you how strong the chain is. So let's take a look at two examples here of significant figures. This is a very inaccurate graduated cylinder. You see a graduation here at 100, you see a graduation here at 200, but no graduations in between. So if we have a measurement, and there's our measurement here, we know that it's somewhere between 100 and 200, but we're not sure exactly where. So we are certain of the one here, the 100. We know it's 100 and something. Now this 5, the 50 here, we're not really certain of that. It could be 40, it could be 60, but we're not really sure of it. And this 0 here is not significant at all, but we do need it in order to get the magnitude of the number. Because I mean, if I had just 15 here, obviously that's not the measurement. It has to be somewhere between 100 and 200. So when we're looking at significant figures, it's everything we're sure of, then something we're not certain of, and then after that, everything else is not significant. But the 0 is necessary. We call it a placeholder. It's there to tell us the magnitude of the number. So this would only have 1, 2 significant figures. So one for the one we're sure of and one for the one we're not. Does anybody have any questions so far? So looking at this second case here, this one's a lot more accurate. As you can see, we've got graduations at 200 and 201. Chris, did you have a question? Okay. I saw someone unmute. So we know that it's somewhere between 200 and 201, so that's a lot more accurate. So we know that we're sure of the 200, so 200 and something, and it's going to be between 200 and 201. So we're certain of the 200 part, but we're not certain if it's 200.0 or 200.1. So this last 0 here, we're not really certain of, but that would be 4 significant figures. So that's a whole lot more accurate. And that's whenever we're dealing with any of these measurements, That's the thing. It's always something that is to a certain accuracy. Now, the thing about this 150 here is that it's not exact. We know that it could be 140, 150, 130. It could be any of those things here, depending on how we eyeball this line, but it's really hard to tell. We're not sure of that number. So none of these numbers are ever exact anyway. They're actually across a range. So it really could be anywhere between 140 and 160. So we just put in 150 as an estimate, and that's where the significant figures come into play. Does anybody have any questions? So that's why they're important, because they define accuracy. So the rules: all non-zero digits are significant, and captive zeros are significant. Captive zeros are zeros between two non-zero digits. So if you've got 932, that doesn't have any zeros in it. That's everything there is significant. 904, that zero is significant because it's between two non-zero digits. Those are easy. Those are the easy rules. Nobody really has any trouble with those. It's these ones here that people have hassles with. Leading zeros, zeros to the left of the first non-zero digit, are never significant. So if you've got something like 0.000932, these three zeros are not significant. 0.00345, the zeros to the left are all not significant, including the ones past the decimal point. That usually confuses people as well. Just looking for my pen here. Here we go. So the reason why are those zeros not significant? Why are they never significant? The one leading zeros, we call them. Why are they never significant? Okay. 0.00932. That's not the only way I could write that. I could write it like this too, quite legally. No problem there. The other way I could write it, (9.32 times 10 to the negative 4). Clearly, three significant figures. So given just a sheer number of ways that I can express that number, you can see why it would be unreasonable to expect that those zeros would ever be significant or have any significance at all, at least to the accuracy. The zeros amount to being placeholders. They're there to define the size of the number, but not its accuracy. So leading zeros are never significant. Does anybody have any questions at all about that rule? Trailing zeros. Trailing zeros are zeros to the right of the non-zero digit. Sometimes they're significant and sometimes they're not. In the case of numbers that have digits past the decimal point, like this number here, 0.009320, these leading zeros are not significant, but this zero is significant. It is part of the accuracy of the number. Whereas numbers that don't have a decimal, like this one here, 34500, or back up here, this 150, those zeros are not significant because those zeros are simply placeholders. Zeros, though, that have been added to something where it's past the decimal point always contribute to the accuracy. Now, the thing is, you might be wondering, well, why is that? Well, let me give you another idea here. So let's say we do have this one. We had 9321. You'd look at that and you'd say, yeah, no worries. That's got 4 Sig Figs, right? Because we got 4 non-zero digits. So the question I would put to you would be, why would you penalize the zero? I mean, make it not even significant. I mean, you're just really just treating it like a 1. I mean, it seems like we're treating zeros differently. But when really, in reality, in this situation with the zero being past the non-zero digits and it being past the decimal point, it does contribute to the accuracy just like that 1 would. So what we're trying to do here is not penalize the zeros unfairly. Does anybody have any questions? Now, the logic for something like 34500 is that I can also write that as 3.45 times 10 to the fourth, and you can see that's clearly 3 significant figures. So that's because these are just placeholders. They contribute to the size of the number, whereas look, this 0 here doesn't contribute to the size at all. It's past the other numbers, so it's just it just contributes again to the significant figures. Does anybody have any questions? Okay, so if you do the soft chalk here, I have some pretty neat interactive exercises that will allow you to make sure that you understand what you've read here. So these are really cool, actually. Some of them are a bit cruel, but they're pretty cool at the same time. Rounding rules. Well, yeah, with rounding, there are some different conventions. I tend to go with the simplest convention for rounding. So let's say I had to take this number here, and occasionally we have to do this because our calculators will often take us out to 9, 10 figures, which is way too much accuracy for most of our purposes, because we're dealing with numbers that are generally 2, 3, 4, 5, maybe significant figures, but usually no more than that. And if we've got a number in our calculator that we need to shorten down to a certain number of significant figures, that's when we've got to do rounding. So if I had something like 0.0862152, like I've got over here, what we're looking at is a situation where the 862 are significant, and because we want 3 significant figures here, and that means we need to look at the next one and determine whether it's 0 to 4 or 5 or more. If it's 0 to 4, then we just know it's going to be 0.0862. We're going to leave that 2 the same. But if it happened to be more than 5 or more, then that 2 would go up to a 3. And I think you're quite familiar with that. Here's an example of that over here. 0.0962, we needed 3 significant figures. The next one's a 7, so we know it becomes 0.0963. Does anybody have any questions about rounding? I didn't really want to spend too much time on that because I think most people are okay with rounding. So here's a rounding exercise here. Tells you what these need to be rounded to, how many significant figures, and then to match that to the ones down here. All right, does anybody have any questions? Any questions? Can I have some acknowledgement that you can hear me? I'm talking to people.
Yeah,
I can hear you.
All right, thank you.
Yeah, we can hear you.
I appreciate it. I just wanted to make sure. Nobody had any questions, so I thought, oh, well, you're either all completely lost or you're all completely with the program. So I'm really not sure which one that is, but I'm hoping it's the latter, not the former. Okay. Calculations. All right, so we've got 2 separate sets of rules for calculations, one for addition, subtraction, and one for multiplication, division, and they are different sets of rules because of the different way that these things are measured. This is not formatting very well because I've shrunk the screen so I can have my other screen over here. I guess I'll go ahead. There we go. I'll put it out for a little bit. Okay. So we've got a plus here and a minus here. The way we handle these operations is, again, our answer to any calculation can be no more accurate than the least accurate number used in that calculation. And the least accurate number in an addition or subtraction is always going to be the one past the decimal point. Whatever's past the decimal point, that's what we're looking for. So when I say DP, I'm talking about digits past the decimal. So we look at 12.620, it's got 3 digits past the decimal, and 6.0, that's got 1 digit past the decimal. So the answer can only have 1 digit past the decimal. Now, obviously, if you put this into your calculator, you don't get 18.6. What you would get would be 18.620. I mean, that's how it would look in your calculator if you put it in. Actually, it'd be 18.62. It probably wouldn't even show you the 0. But I'm just going to leave that in there for kicks. Now, we know that the answer can only contain 1 place past the decimal. So we look at that, and that's going to define our rounding. So that's why it becomes 18.6, because the next digit is a 2, so we'd round that to a 6. Does anybody have any questions? Right, same deal over here. We've got 3 places past the decimal, 7 places past the decimal. Obviously, we get a longer answer than this in our calculator. We cut it down to 3 places past the decimal. Does anybody have any questions about
Why
that?
do you cut it down again?
It's because the answer to that problem can be no more accurate than the least accurate number used to get that answer. And the accuracy is determined by the number of places past the decimal. So the more places we have past the decimal, the more accurate it is. This is a very accurate number because it's got 7 places past the decimal. This one only has 3, so the answer can have no more than 3.
Okay.
Is that right? Okay.
Yeah, that makes sense.
Okay.
But it depends on each problem, essentially.
Well,
what the problem is.
Whether it's, well, only if it's addition, subtraction, or multiplication, division.
Okay.
Okay. Now, I do have, again, some exercises here to help you with that, and they're not too bad. I would recommend doing this. It's fun. It's a fun way to make sure that you are understanding what you need to do. Now, multiplication and division, the rules are a little bit different. It doesn't go by the number of places past the decimal. It goes... This is unfortunate. I don't know if you can hear that. That's really annoying. Well, folks, listen, I'm going to have to... Looks like I have to exit the building. There's a... looks like the fire alarm's going off. I don't know if it's a drill or what the story is, but I'm going to have to leave here for a second. I'm hoping to be back here before 15 minutes are up, and I'm really sorry about that, but if I don't move, somebody's going to make me move. So I will be back, okay, hopefully. As long as the building doesn't burn down, I'll be back. Sorry about this.
uh,
All right, folks, I'm back. Sorry about that.
You're alive.
I didn't start the fire, and there wasn't really a fire. So that's why they've let us back in, which is good. I do apologize again. Not much can be done about this, unfortunately. All right, how many people we still got here? Oh, everybody's still here. All right, that's cool. All right, thanks for staying around. Appreciate it. I'm sure you've got other things you were doing as well, multitasking, waiting for me to come back. All right, so we're looking at multiplication division. So with the addition subtraction, I said it went by number of places past the decimal point, but with division and multiplication, it goes by the actual number of significant figures. So this has got 3 Sig Figs, this one has 5 Sig Figs, the answer comes out to 3 Sig Figs. Again, in the calculator, let's see what that would be. I'll just do this one here. 4.01 times 62.753, and it comes out to be 251.63. I'll go ahead and write that down. Just write it over here, 251.63, actually I'll 953. So that's what's in my calculator. So what I do is I look at that and I say, well, I've got 3 Sig Figs up here. I've got 5 down here, which means my answer comes out to 3, which makes it 252. And that's how I do it. And that's how they're all done pretty much when you're dealing with multiplication division. Anybody got any questions? All right. So I've got another set of problems down here. They're fun. You can do those to check your understanding. Okay, there's a worksheet here which does have answers associated with it. So you can do that and check your answers. All right, does anybody have any significant figure questions here that they want to talk about? All right, I'm going to just show a couple of these problems here. We'll do this one here first. We'll do something fairly simple. So starting out, converting 4.00 inches into centimeters and how we would handle something like that. So I like to use the dimensional analysis method, which means for something like this, just showing you how it would work out, you do, whoops. I have to pull this over here a bit. Get my brushes back. Okay. Okay. So 4.00 inches, and we want to go to centimeters. So what we'd be looking for here is we go back to our sheet, our conversion sheet. Now you'll have this on the test. You won't have to memorize any of this. I have to go back to it. Let's see, where is it? Pull this over here. Page 2. Okay. So what I'd be looking for is some sort of relationship between inches and centimeters, because that's what I want. And I do actually have something here that goes directly from inches to centimeters. So I know it would just be a one-step process. So it'd be 4.00 inches, and then I do a line. Then what I like to do is I like to put the units in here first, and then put the numbers in. So inches goes on the bottom, and the reason that is so that they can cancel, and the centimeters goes on top because that's what we want. And then I know what the relationship is. It's 1 inch is 2.54 centimeters, and then I go from there. Does anybody have any questions about the setup? Okay. So the answer there comes out to be 10.2 centimeters. I think it's 10.16 or something. Let me clear that out here. 4 times 2.54. Okay, it comes out to be 10.16. And then what we do is we look at the number we started with, look at the number of sig figs there. That's the number of sig figs we generally have in our answer. Now, as a guide, you might be wondering, well, how do you know when to use the sig figs from conversions? Well, you generally won't have to. And the reason for that is because when you're looking at these conversion factors, anything here like 1 kilometer, 1,000 meters, 1 meter, 1,000 millimeters, those have infinite significant figures because those are counting numbers. They're considered to be exact. Something like this, that's got the 3 dots after it, means that there's plenty, there's more digits to come, but we've only just reported those number of digits. So you'll notice for something like this, 1 liter is this many quarts. 1, 2, 3, 4, 5, 6, 7, 8 significant figures. Incredibly unlikely that your starting number is going to have more than 8 significant figures. So the chances are you wouldn't even be concerned about that as far as affecting the significant figures. So it's generally, 99% of the time, it's going to be the number out the front that's going to determine the number of significant figures you have in the answer. And that was the story over here with the one we just did. So 3 sig figs comes out to 3 sig figs at the end. It was 10.16. We rounded it to 10.2. The 2.54 here is also infinite significant figures. That's an exact number as well. Does anybody have any questions? Any questions? Okay, so something like this one here, what if you know that you're going from feet to centimeters, but you go to your conversion chart over here, we're going from feet to centimeters. There is no conversion here that goes directly from feet to centimeters. So we know it's going to be more than one step. And actually any problem that I give you can be done in 2 or less steps. You never have to go for 3 as far as I can tell. So what we'd be looking for here is a way to get from feet to centimeters. And what I would do is look for conversions that had feet in them. There's only one actually. This is one. 1 foot is 12 inches. So I know I need something to go from inches to centimeters. And we already did that. And that would be 1 inch is 2.54 centimeters. So those are the 2 sets of conversions we're going to be dealing with here. So let's go back and see how we would set that up. Okay, so it was, let's see. We're going from 15.2 feet to centimeters. So that's what we start off with, is 15.2 feet. Then I do times, and then I do times. Now the reason I know it's 2 steps is because I don't have something where I go directly to centimeters. There is no conversion for that, not directly from feet to centimeters. It'd be easy if it was, but there isn't. So I know centimeters is going to be at the end. I also know feet are going to be down here because they have to cancel. So what we're left with is trying to figure out what unit goes in to these blank spaces here on the top of the first one and at the bottom of the second one. And those are going to be the same unit. It's going to be inches because that's our unit that we have on the conversion chart that allows us to link those together. So again, inches, centimeters, feet, inches. So we know inches is what's going to be there. And then what I can do is I can use this conversion chart to fill in those numbers. So I know it's going to be 12 inches and 1 foot and 2.54 centimeters and 1 inch. And then when I figure this out, I get 463 centimeters. In my calculator, it's going to be something a little bit different, I imagine. Let's have a look. Yeah, I get 463.296. This one has 3 significant figures. Right, we're dealing with multiplication division here. So our answer comes out to be 3 significant figures as well. Does anybody have any questions about this? Okay. All right, I would have gone into density a little bit more thoroughly than what I'm going to do right now. But I'm going to just concentrate on the more difficult parts of density. Most of it is pretty simple. We know that density is mass divided by volume. Let's take a look at that. Here we go, Module 4 soft chalk. So it's only 6 pages, as you can see, so it's fairly short as far as modules go. So density is mass divided by volume, and what that means is we've got some different ways that we can express density. So density, whoops, again. Okay, density equals m over v. That means that volume is equal to mass divided by density. And we know that mass is going to be density times volume. So those are all good to know. It's all good to know those three equations, those three different things. Depending on what you're looking for, that's how you're going to get them. The density itself can be grams per mil or grams per cubic centimeter, because a cubic centimeter and a mil are the same thing. So either way, you'll see that expressed that way. The other way you'll see these expressed is gml to the -1 or gcm to the -3. So whenever we've got a negative power, it means it's been divided by, it's on the bottom of something. So, but those are all equivalent statements, every last one of them. Now, whether you use mils or cubic centimeters is often dependent on if you're given mils or if you're given centimeters or something like that in order to figure out the volume. Does anybody have any questions so far? So those are the main things I want to focus on at this point. Oops. All right, I'm going to leave it to you to do the volumes, masses, densities. They're not too bad. All right, let's look at a situation where we've got a density of a cube with side 2.1 centimeters and a mass of 34.0 grams. So we need to figure out the volume of a cube, and the volume of a cube is side cubed. The volume of a block is length times width times height. The cube is just a rectangular prism that all the length, width, and height are the same. So cubed, so 2.1 cubed is going to be the 2.1 centimeters, and all of that's cubed. And what you get in your calculator here would be 9.261. To get the answer here, you can go ahead and do that, 9.261. You can plug that in. It's probably a good idea to plug that whole answer in and not to shorten it down to two significant figures at this point, because then you're sort of double rounding. So what you would do is you do the 34.0 grams, divide it by what you get for the 2.1 cubed, and you would end up getting 3.7 grams per cubic centimeter. The reason it's down to 2 sig figs is because when you look in the problem, that has 2 sig figs and that has 3 sig figs. So you go back to the problem and you look in there and you say, well, what has the smallest sig figs? That's going to be the sig figs in my answer. So that's why it comes down to 3.7. Obviously, it's going to be many more figures than that in a calculator. Let's have a look at what it would have been. 34 divided by 9.261. Okay, oh, hang on. Sorry, try that again. There we go. So it comes out to be 3.6713097994. That's how it looks in the calculator. I shorten that down to 2 sig figs because in the problem, that's what my least accurate number has, is 2 sig figs. So that's what we get down here. Does anybody have any questions about that?
What is the difference between grams over milliliter or grams milliliter minus 1?
There isn't any. It's
I
the
don't.
same thing.
There isn't any.
Yeah, it's the same
Well
thing.
then. Okay. Well then, what is that? What does the -1 exponent symbolize? What does that mean
It's on the bottom.
necessarily?
Yeah, it's on the bottom. Per mil / mil. So the rule I'm kind of working from is this: if you've got, well, let's see, let's say a to the x over a to the y equals a to the x minus y, right? So if you've got a to the 0 over a to the y, that equals 1 over a to the y, which is a to the negative y.
Hmm. Okay. Okay.
Okay, I mean, this is one of those power rules. You know, ax times a to the y equals a to the x plus y as well. You know, when it's the same base.
Right. Okay.
So that's where that's coming from. David, I'm sorry about that. I don't think I had the chat box up here. I don't know if you were trying to get into the chat box. Is anybody trying to get into the chat box? Let's have a look.
No, it's fine for me. I'm just using my phone for Zoom instead of the computer.
Okay, here we go. Yeah, that's right. Okay, you better believe it. Okay, let me get this down here. Oops, I don't want to close that. Let's go back to what I'm trying to do here. All right. Can you also see my screen, or did I unshare? I think I unshared. That's what happened. Let's try that again. There we go. There we go. Back in business. But if we're dealing with centimeters, it makes more sense to do grams per cubic centimeter rather than grams per mil. Even though they're the same thing, it makes more sense. Because what we're doing is we're cubing the centimeters as well. It's 2.1 centimeters times 2.1 centimeters times 2.1 centimeters. So the centimeters all get times together as well. And that's where we get the cm3 as the unit. But you'll also notice, David, just to piggyback on your question here, that grams cm to the -3 would be the same thing as well for the same reason. Again, it's the power becomes negative because it's on the bottom. But that's the main thing. It's not a difficult problem, but you know, it's the Sig Figs that really are most important there. So if you have a rectangular block, same kind of deal, 2.5 centimeters, 3.60, 5.90. To get the volume, we multiply all those together, and the centimeters all multiply together to give cubic centimeters. And then, you know, again, I'm taking this out to the max number of significant figures, even though I know this only has 2, because I don't want to be rounding twice. So I don't want to put 53 in here and then have to round again at the end. So what I do is I leave all of those figures available, and then I go ahead and do 50.0 divided by whatever I get in my calculator for that. And then I shorten it down to 2 sig figs because that's the smallest number of sig figs in my measurements over here. Does anybody have any questions? Okay.
So you shorten the sig figs when you're multiplying to the one of the lowest, basically.
In the problem, yeah.
Is it with every multiplication?
Yeah, yep, yeah.
Okay. What about division?
Yeah, same deal.
Okay.
Same deal. But only in multiplication and division problems. So see, this is all multiplication and division. There's no hassle with that. But David, I'm going to show you an example now where we do addition subtraction as well. And that's going to bake your noodle.
Oh. Okay.
So let's take a look. This is an example here. It's a fairly simplistic example. I think it makes a lot of sense from an intuitive point of view. You do this in the lab as well, or you would have done it in lab in Intro to Chem. I think you do it in lab in General Chem as well. There we go. So it's the same kind of deal. We talk about brushes. we talk about this situation where we've got a graduated cylinder and we stick some water in there, and then we've got an irregularly shaped object like a stone or something, which we put into the water, and of course the water will go up by the volume of whatever the stone happens to be. So this volume here would be the difference, and that's going to be the volume of the stone. Is everybody okay with that? Anybody have any questions? So if you're given something like this, 12.3 mils of water in the graduated cylinder, so that would be the situation here, 12.3 mils. And then, I don't know, for some reason, we don't see the graduations. It comes out to be 15 mils. So this is actually a less accurate number. The new volume reads 15 mils. What's the density of the stone? So we do what you'd expect to do. We do this volume final minus volume start, 15 minus 12.3. But the problem is, because the 15 is less accurate than 12.3, this is going to go by the number of places past the decimal point. So this has no places past the decimal point. This has 1. So this comes out to be 3. So you can see the difference already here in this problem is that I actually have to get the significant figures from the subtraction first before I go down and do the multiplication division. I call this mixing operations. We're dealing with different significant figure rules, so I have to account for those first before dealing with the multiplication division. This leads to all sorts of problems for students because they see it as being inconsistent. I don't blame them. It's not very nice, but it is what it is. Does anybody have any questions about this, especially compared to the previous one I just looked at where I didn't do this? I just went in and looked at the number of Sig Figs.
What was the issue with this problem that made it specifically difficult? I didn't hear that part.
The fact there's a subtraction involved, David.
Oh, okay.
A subtraction is going to be different rules to the division multiplication that we looked at previously. If you remember, subtraction goes by places past the decimal, not by number of significant figures.
Mm-hmm.
So when we do that, we come out to 3 mils, which is actually 1 significant figure, which means our answer comes out to 1 significant figure. Not pleasant, but that's how
That makes sense, though. That makes sense.
Well, a lot of it might make sense now, David, but when you're doing the problems, it might not make sense.
Okay. Okay.
All right. Does anybody have any other questions? Okay. So I've got a problem here that goes through and allows you to set it up and everything. It's kind of like what you go do in the homework as well. So the other kind of problem that we look at is, you see, this is finding the density of a irregular solid like a stone. We can also go ahead and find the density of a liquid by using an empty graduated cylinder and then filling it and then weighing it. So this has a certain mass, and then after it has liquid in it, it has another mass. And that means that we can easily measure the mass of the liquid, which is going to be the difference between the two masses. The volume is measured because we have it in the graduated cylinder. Again, this is something you would have done back in Intro to Chem Lab. You might have even done it, I don't know, have you done it this week or next week? Maybe you're doing it next week in lab? Probably next week in lab. I think you're doing physical chemical properties this week, and you'll be doing density next week. All right, and the same deal. So we've got the empty graduated cylinder, 150.0 grams, and the full mass, which is 175.05. Now this is going to go by number of places past the decimal. So we do is 175.05 minus 150.0. We end up with 1 place past the decimal, which is why it's 25.1. And then we use that as our mass and divide by the volume that's in the problem. So that comes out to be 3 significant figures because that's 3 Sig Figs and that's 3 Sig Figs. Does anybody have any questions? All right, that's the most confusing part. You know, that's really what I had wanted to go through today. Let's take a look. We'll go to the homework here, and you can see the kinds of things you'll have to do in the homework. And we'll go over here. All right. I want to point something out. Let's go back to Module 3. The assignment for that is relatively easy. I'm not going to open that up, but I will open up the practice quiz here and show you something. So the way these are set up, you actually have to type stuff in, and you type it in directly off the conversion chart. And you do have to use the numbers exactly as they appear. So if you remember what I was talking about, how, well, let me, I have to open up another window here so I can pull up the Module 3 thing again here. I don't want to close that quiz out. Open up the soft chalk here. Okay. You have to type in every single digit without the dots here, because that's how many significant figures we're given for all of those. So you can't just say 1 liter is 1.05 quarts, make up whatever you want for that. It has to be exactly what's on there. That's why I've got that in the directions as well. So just make sure everything gets typed in. Now, the other thing is that the answers do take significant figures into account. So if you get 9 out of 10 for a problem, chances are you have just got the wrong significant figures. The answers will appear. Let me show you what the answers look like. I'll submit the quiz. You can do this too on the practice quiz. So you can see exactly what formatting I want. There you go. So these are the actual answers that are accepted, but the answers don't have parentheses on them. So it's either going to be this or this. So that's not the entire answer. It's whatever either one of these will work. So for something like this, these are fine. These answers would be fine as well. Now, sometimes I haven't got it here, but in the credit quizzes, you've got all these different answers that have different numbers of significant figures, and those will have different amount of credit for them. So the ones that are correct will give you full credit, whereas the ones that are incorrect will give you less. So that's why you might see an answer that's been marked correct, but you get fewer points, and that's because it's got the wrong significant figures. Does anybody have any questions? Okay, so that's what you're going to see.
To be clear, these homework assignments and quizzes are all due, I think the day before test 1, right?
You have a day before test 1 is due, but that doesn't mean you have to wait till the day to do test 1 either. You can do test 1 before, and I'd recommend it because then that tells you how much homework you need to do in order to get the grade you want. That's how I do it.
How many attempts do you have on test 1? Just 2 or 1?
You know what? I can't remember, David, off the top of my head. I will check.
Do you mean like the test 1 practice, like the unlimited attempt? Is that what you mean by trying it early?
No, I mean actually doing the test early.
Oh, okay.
So I mean, obviously, in order to do the test, you'd want to do the practice, right?
Yeah.
Beforehand.
Of course.
But I'm saying do the test early so that you know how much homework you need to do. Gosh, if it was me, that's what I would do. I'd be all over that.
Yeah, but aren't the soft chalks counted as graded assignments?
No, they're not.
Oh.
No,
well, then are the quizzes counted as graded assignments? What are the graded assignments for each module?
It's just the credit quizzes. That's it.
Okay.
You can look.
So the rest is just practice for the test.
Yes.
Okay.
But the credit quizzes are actually part of your grade. You can look in the syllabus. It'll show you exactly how you get to them. You have to do the assignment, then you have to do the practice quiz, then you have to do the credit quiz. You do that.
All right. Thank you for clarifying.
Okay, no worries. So looking at what was I going to show you here? So looking at the sample test here, oh sorry, the test. I was going to you asked me how many attempts there were. That's what I'm looking at. Okay, let's have a look. Assessment. See how many attempts. One. You get one attempt.
Okay, so then maybe you don't want to do the test early, but you want to do the sample test early.
No, I would want to do the test early too, David. I would.
Really?
Yeah, because the homework and the test make up the grade. So let's say you get 90% on the test. That means that maybe you have to do less homework to maintain your grade of 90%. But you don't know how much homework you need to do until you've done the test. Do you see what I'm saying?
Yeah, but okay.
Well, it's only one day.
I think it's a better idea to not risk your one attempt on the test before you've fully done all of the homework assignments and the soft trucks and everything. But that's me.
Yeah, well, do it all early then.
Yeah, that's the plan.
All right, fair enough. Let me go back here to module 4. Oh, actually, we're out of time here. All right, but yeah, I will show you something quickly on module 4, and then we will call it a day. I'm really sorry about the whole fire alarm thing. A lot of stuff beyond my control going on here today and Monday. All right, let's go back to, oh, sorry, module 4. It's in test 1. Just something very quickly in the assignment that I wanted to point out here, because sometimes people get confused about this. It'll only take me a second. All right, so if you have something like this where there's a multiplication, 1 times 2, then technically this would be density times volume to get the mass. But density or the volume could go in either spot here, technically, because it's a multiplication. But I actually have it arranged. I've put the volume in space 1, and you can see that here. I just wanted to point that out. Sometimes people do it the other way around. They wonder why they got it wrong. And it's just because I have already assigned a slot to something, and then you assign the slot to the other thing. So just be aware of that. That's all I wanted to point out. Okay, so we will call it a day, and I will see you hopefully next Monday without any dramas going on here. If anybody wants to hang around, ask me some questions, they're more than welcome to. For all the rest of you, bye.
Have a good day.
All right, no worries, David. See you later. All right, is there anybody left here who has a question for me? Haley, Kaloni, David, Alicia, or Jackson? Actually, I think there's fewer people now, down to 5. Anybody else? Anybody have any questions? Any questions? I'm going to assume that these folks are no longer at their computer. I will see you all later. Bye.